Hello, my name is Tan Tran. I'm one of the co-founders of GameSalad. And today I wanted to talk about the importance of social distancing. And what we're going to do is we're going to illustrate it through a game simulation. With all of us stuck at home, it's kind of a good reminder of why we are isolating ourselves and to help keep too many people from getting sick at once. This idea is based off an article from the Washington Post, and I'll link it below. But let's get started. So what we're going to do in the simulation is first, we're going to need to have people to wander around it. So let's go into create an actor in my new project here. And what I'm going to do is use a timer. The reason is I want this person to randomly change directions and move in a different direction every second. To change their movement, what we're going to do is change an attribute on self, which is this particular actor. We're going to change its motion. And in that motion, it's linear velocity on the x-axis to a random number. Now, the thing is, the random number generator in GameSalad can only return positive integers. So what we're going to do is we're going to do return 0 and 2. And as a trick, this is how we're going to get a negative integer. We'll subtract 1 from 0 and 2. So if the random number generator returns a 0, you'll get -1. If it returns a 1, you'll get 0. And if it returns 2, you'll get 1. And then we'll multiply that by 100 because moving 1 pixel a second is very, very slow. So let's update that. We'll do the same thing for, not accelerate towards. We'll do the same thing for the y-axis. So self, motion, linear velocity, y, and then we'll do random 0, 2, -1 times 100. Woo. All right. So now let's get into the scene and let's throw our actor onto there. Oh, wait, one more thing. The actors are sized 100. I'm going to make them size 20 by 20 because that way we're going to have 100 actors on this in the simulation, and so making them smaller means that they'll more things can fit on the screen. Let's drag an actor into the screen, hit preview, and we can see the actor nope, it's not randomly moving around. So I must have done something wrong. Let's go back and take a look. First off, let's go take a look at the actor and let's look at the function because that's probably what's going wrong. It seems to always be going in the bottom right direction, which implies that the x and y values are both negative. And then when I look at this, I'm reminded of the fact that expressions follow the same order of operations as you do when you learn in arithmetic or math class. So multiplies happen before additions and subtractions. So what's happening here is we will have 100 times 1, and then that's going to be subtracted from a random number between 0 and 2, which means our randomness is now between -100 and -98, which is not what we want. So we can use parentheses to enforce our order, the order that we want, which means that the random and the subtraction of 1 happens first, then it gets multiplied by 100. So if we do that, and then we hit preview, we'll see their actors now moving as random direction every second, sometimes standing still. The other thing I would like to point out, something that I had done before in this setup, so I forgot to mention. In the scene, you'll want to ensure that wrap X and wrap Y are checked. That way, if they go off the top of the screen, they'll come off the bottom. If they go off the left, they come back the right, which is kind of a simulation of a mini world, which is great. So let's go back to our actor. I'm going to name this person so I know what I'm dealing with. Let's go and I could drag 100 different people and randomly put them around the screen, but that's a lot of work. So instead, I'm going to let the use programming to do it for me. So I'm going to add another actor. We'll call this actor the MCP, the Master Control Program. This is where we're going to keep any logic not specifically related to a person or the people in the simulation. So what I want to do is add don't want to do a timer, because what I want to do is show, like, make 100 people at once. And when you want to make 100 people, you use a spawn behavior, or you want to make a single person, you make a spawn behavior for an actor. So now I'm going to make one person, and I want them to show up randomly on the screen in a random position. So let's say we'll take the random, and they want to be anywhere from 0. This was for the x-axis, so we'll do the devices screen size width. So along the width of the screen, anywhere it can show up anywhere between 0 and the width. And then same thing for the y-axis. Random 0 devices screen size height, since up and down. So now a single person will spawn. If you want to do something multiple times in a program, what you'll often use is called a loop. And GameSalad has a loop behavior. So let's make sure the spawning happens in the loop. Oops, why aren't you dragging? There we go. There we go. So now we need to define the conditions of the loop. The idea is, if you don't say anything, a loop in theory could just run forever. We'd have an infinite number of people spawning in the game, and it'll probably crash the simulation. So what we want to do is let's add a variable to track the population of the game. So I have an integer. We'll call it population, and we'll make the population that start at 0. So what we're going to do is the game population. We want to make sure that while the game population is less than 100, we'll spawn an actor. So what this means is that as long as there is less than 100 actors on the screen, it'll keep spawning new ones. There's a problem with this, though, which is we haven't changed the population anywhere. The person has nothing that's changing the population, and neither does NPC. So let's add a change attribute so that every time we spawn a person, we're also going to change the population to game population plus 1. So now when we create these 100 people, there will be randomly, basically we'll create a person, increment the population, and spawn a new or we'll create a person and increment the population, so that the next time it comes around, then the population is 99 or 2, which is still less than 100, and it keeps going until there are 100. And once we get over 100, the loop stops. So let's see if this works. Oh, nothing's happening. I wonder why. Well, it's because only things on a scene actually get executed. So I'm going to put my NPC into the screen, and I'm going to make it a little smaller so it doesn't take up a lot of space. So now when I preview, you get 100 random people showing up on the screen and wandering around. Great. So we don't need this one person anymore, because the NPC will spawn them all for us. So the next thing is we're going to need to simulate a sick person. So let's make another person. Let's make a infected person. We'll call them infected because many diseases you could become infected with the disease but not actually show any signs of sickness. So we'll just call you infected instead. We'll also want you to be 20 by 20, but let's make the infected people another color, maybe an unhealthy shade of green. So we got a person, and we also want them to move in the same way. So I'm just going to copy and paste the timer. And actually, I'm going to name the timer wandering, so I know what these timers mean when I'm looking at it really quickly. So now we have a sick person that wanders around too, and they're green. How do we make a person sick? Well, let's go into a person. What happens is we'll have a rule that whenever they collide with a sick person, they too will become sick. And how do we make them sick? Well, because we have two separate concepts of an infected person and then a person, what we're going to do is destroy ourselves and turn ourselves into a sick person by spawning a infected person. The order inside for rules and loops, the order of actions actually matters. So what we want to do is we want to spawn the sick person before we destroy this actor, because if we destroy ourselves before we spawn the person, then the spawning will never happen, right? So let's do that. So we'll spawn another sick person every time that happens. And then the other thing is we want to track the number of sick people. So let's add an integer. So let's call this the infected population. And what we'll do is we'll change attributes so that the infected population increments because it makes the infected game population plus 1. So what we've done is now every time we run into a sick person, we're going to create a sick person, increase the number of sick people, and destroy ourselves because we're being replaced by effectively a sick person. So what I'm going to do to demonstrate how this works is let's add one sick person into the middle of our map and then hit preview, see what happens. So as you see, every time a sick person touches a person who is well, they become sick themselves. And over time, the population starts getting sicker and sicker. Now, we want to see the number of people that are sick versus the population. So let's really quickly add a display text on the NPC, since we already have it on the screen, and we'll make the display text show the game infected population. We'll make the font a little smaller because our box was a little small, so let's make it 20. And preview. So basically every new person that's infected will increment the perfection calculator, and you'll see it there. So one last thing, you notice that we started in 0, but we added a sick person into the game already. So let's just make sure that infected population starts at 1 with the one we added. The next thing that we want to do is let's have the program graph for us the number of sick people so we can quickly see over time how the population of sick people changes. What I'm going to do is add an actor called, let's call it graph bar, and we'll make it 20 pixels wide. So it'll be a little bar. We'll make the bar purple. You can choose your own color, but I'm going to make mine purple. So you'll have a purple bar on the screen. And then because it's a bar graph, the idea of bar graph is along a given axis, the bars will change size to indicate the important data over an axis. So in this case, we want to change the height of this bar, not the game, but the self size height to match the game infected population. We'll update that. And then what we're going to do is we'll have the NPC program create these bars over time. So since it's over time, let's use a timer. And every second, we will spawn a graph bar. We'll do it at the bottom of the layer so that the graph is always under all the simulation. And then we'll make the bar show up relative to the scene because we don't want it to show up in the top right corner near the NPC. We want to show it at the bottom of the screen. So it'll be 0, 0. Every second, we'll see the bar change. So if we hit preview now, Nope, here's my bar. So every second run to completion, we will spawn a bar graph at the bottom of the layer, and then the graph bar will set its own height to the infected population. Maybe the graph is too small, so let's pick a number, make the graph a multiple of the population, and so you see this little bar. I see it now. There's a little purple bar there that's slowly getting bigger as the infected population increases. But it's only showing up right there, and we want to see it over time. So let's go back to the NPC, and in the game, let's add a counter for the number of bars we have on the screen. So that kind of represents, in its own way, time. Bar count. And then every time we spawn a bar, we're going to change the bar count. Game bar count to game bar count plus 1. The other thing we're going to do is we're going to change the position of the new bar actor every second. So let's make it game bar count times 25, because the bars themselves are 20 pixels wide. So every 25 pixels, if we put a bar, that will give a little spacing. So we do update. Now when we hit preview, we can see that every second a new bar shows up, and the bar represents the population that's sick. And as more people get sick, the bar gets higher. So as the more people get sick, it starts increasing exponentially until we taper off as the whole population is infected. All right, so that shows you how quickly a population can get infected from one person. Now let's simulate social distancing, and let's find a way to slow the spread of the infection. What I'm going to do is make it so that randomly a person will not move. So we have this wandering. One way we can do that is, so let's say one in every 5 people to move instead of every person to move. So let's create a rule. And the idea is we'll make, what's the best way to do this? Well, so there's an interesting feature in GameSalad. An actor can have its motion with a max speed. So let's enforce a max speed. And right now the max speed is 0. What's going to happen? Let's make the max speed 200. So what we can do is we can randomly change your max speed when the person spawns, and make it so that only 1 in every 5 people change their max speed. So I'm going to have a max speed over 0. So let's change attributes, and what we can do is we can do self motion max speed. We'll do a random function, but we want to do a random 1 through 5, but that's going to give us a max speed of 1 or 5. So how do we make it so that we have only 1 out of every 5 people show up the max speed? We need 4 out of these 5 values to be 0. There's an interesting trick here where if you divide the random number by 5, so then if you get 1 divided by 5, it's 1/5. And if you did 5 divided by 5, you get 1. Then what we can do is we can round that number. And so if we round it, then let's do some calculations here. Go to my Google Sheets and create a new sheet real quick. So I have 1, 2, 3, 4, 5. We'll divide all those by 5. Then we'll round the values. So now we've got 2 out of 3 values equaling 1. What we want to do is get all the value, or we only want one of those values to equal 1. What happens if we say subtract 0.5 from the previous value? Get -3, -0.1, -0.1, -0.3, and 0.5. Then when we round this value, we can see that now we found a way to randomly choose a number between 1 and 5 and convert that from between and lock it to 0 or 1. So let's do that. We'll do random divided by 5 times, or subtracting 0.5. And to ensure our order of operations, let's add some more parentheses. So first we'll take a random number, divide it by 5, and subtract 0.5, and then round it up. And when we round it, that means that there's a 1 in 5 chance that this person's max speed will be 1. We want their max speed to be higher, so let's make their max speed 200. So now, when we preview the game, all these people show up, but not everyone is moving. And as you can see, because fewer people are moving, the infection is spreading much more slowly than before. Now, the other thing you notice is that everyone at 6 starts moving, which is part because we only had this happen on sick people. So let's make sure, or on well people. So let's make infected people work as well. So now when we go back, sick people aren't suddenly moving, or aren't always moving, only some of them will. And so now that social distancing, the idea that we all stay in, move as little as possible and keep away from each other to avoid infecting, you can see now over time the infection spreads much, much slower. It still spreads though, and so we need to look into other things. Let's see here. So random. Oh yes, we also need to make sure the infected person enforces their max speed as well. So let's go into motion, enforce max speed, make your initial max speed 200, and you'll see that even if we have a well isolated infected person, then everything the disease spreads very much more slowly. And you can see that the importance of having social distancing. It slows the spread of the disease. The other thing we can see is that the disease will we don't want to be depressed and have everyone sick forever. So let's start making people well. Let's add another concept of a recovered person. Let's make someone who's recovered blue. Actually, you know what? Tired of everyone being colorless. Let's make everyone blue, and we'll make a recovered person yellow. No, orange. We'll make a recovered person orange. Okay, so let's say the infection cures itself over time. So we'll add a timer, and let's say after 5 seconds. Yeah, let's do 5 seconds for now. Actually, let's make it last longer. We'll make it 15 seconds. So after 15 seconds, an infected person needs to become a recovered person. So let's do the same thing we did before. We will spawn a recovered person to take our current person's place, and we will destroy ourselves, but we'll also remember to change an attribute so that the game's infected population decreases by 1. So game population -1. So let's make sure that happens before we destroy ourselves. So after 15 seconds, we will change the infected person count. We will spawn a recovered person, and we will destroy the infected person. And so we need to make the recovered person act like a person. So we will want them to wander. We will want them to randomly be still or not. But we don't need this rule. Now, since I didn't comment it, I had to open to see what it was, but this is the infection rule. We'll just say that the recovered people are inoculated. They can't get sick again. That's not true of all diseases, but it is true of many diseases. So I'm going to copy and paste the max speed, and I'm going to copy and paste the wandering. And so now we have a recovered person that wanders. So now if we do a preview, we can see that the infective people slowly increase over time because social distancing is keeping people apart. In fact, we have one infected person that is our recovered people are very big. Let's fix that. Let's make sure our recovered people are 20 by 20. And actually, let's go back and show something. We will allow, we're going to label this. We're going to turn off social distancing. On and off here is a way to debug the game by showing how social distancing changes, or by turning behaviors on and off. So if we turn off social distancing, so all the well people are moving around like crazy, eventually they will start infecting other people. And we'll see the number of infections rise. Now, the nice thing is in this simulation, the sick people tend not to move as much. And so that also helps slow the spread of the disease. But you can see that the disease is spreading and it's getting harder. And over time, as people get well, as represented by the orange people, you'll see those who can't get infected. And so we limit the population to get sick. And so we can see that unlike before, when everyone was moving around, even sick or not, the number of people slowly spreads. Or the inspection, the let's say the population of people sick is keeps in a manageable level. But if we have everyone move, so let's turn social distancing. So let's make the sick people also wander around, and let's make the recovered people. I think the recovered people also all wander around. So we turn off social distancing for everyone, and we can see what happens. We can see when everyone's moving around. Eventually, as people get sick, the infection starts to spread. We can see this exponential curve that grows until the population stops getting more infections and it starts tapering off. We can also see by colors that everyone is either sick or recovered, which means everyone at some point had gotten the disease. Now let's take the effects of this simulation without social distancing, or with social distancing. So now we'll turn it on for everyone, which means that, again, 1/5 of our population won't be moving around or will avoid moving. And let's preview. Now we see while most people stand still, we do have one sick person who's wandering around spreading the disease. But if you notice that most of the people who get sick don't spread it to other people because they're standing still. And you can see that the growth of the number of sick people is much, much smaller and stays in a very manageable level. In fact, we may even get to the point, if we're lucky, where there are people that never get sick at all because everyone gets cured before they get a chance to spread the disease even more. And there, the last person that was sick is now no longer, there's no longer anyone sick. And you can see that there was very few people who caught the disease over time. And then one last thing to make it more interesting is we are going to change it so that the infection person will always be moving if they're one of the first few people. And that's to make sure that the simulation's interesting. In the last version you saw, it worked really well. But I've run this a few times, and sometimes if the initial sick person or infected person doesn't move, then there's very, very little change in everything. So let's add a rule that ensures that at least the first infected person will move. And what we're going to do is add a condition based on the infected population. So we'll take the game. No, not bar count. Let's take the game. Infected population. While the infected population is, when the infected population gets greater than say 2, we'll start implementing social distancing on the infected population. That'll guarantee that at least the first 2 people start moving around to spread the disease. Which makes the simulation more interesting, but is not necessarily realistic or not, depending on how you look at it. So then we'll probably get something similar to what we saw last time, because the first 2 people are moving, and in an unlucky coincidence, they hit a very large cluster right away of people. So now they're still spreading the disease, but as you can see, with most of the people standing still, they don't spread the disease very quickly. And the curve for the increase in number of people is it basically doesn't hit everyone and is much smaller and gives time for people to heal, or time for people to heal from the infection and not spread it. So again, social distancing does a lot to stop the infection. So many of us have been asked to stay at home and to distance ourselves from people. It can be hard to imagine why this is so important. With a little bit of programming knowledge, we can give ourselves the tools to understand the world better. Through this simulation, you can see how important it is that we stay at home as much as possible and keep our distance from each other in public. Scientists use similar, if much more sophisticated, simulations. You can even do things to make this simulation more like the real world. For instance, diseases don't instantly infect everyone they touch, so you can make the infection rates based on a random probability. You could also increase the chance of someone who is sick not moving, so that well people move more and sick people move less. I'll leave it to you as an exercise for you to come up with your own ways to make this simulation more interesting. I hope this exploration into game simulation has helped you make sense of our current situation and given you the inspiration to keep up the good fight. You're not just stuck at home, you're playing an important part in saving lives. Thank you for doing your part to keep the spread of the disease under control. Keep safe, keep healthy, and keep learning. Thanks.